All right, welcome everybody. This is going to be the tutorial video for section 7.1 day 1 on exploring exponential models. So what I'm going to start by doing is sharing my screen so that you can see the handout. You can either use Cami to take your notes, you can have this printed, or you can do it in a notebook. Again, my suggestion would be if you have a printer to have printed this out so that you have the guided handout in front of you and can be writing and having the video up on your Chromebook. All right. We want the Word document. Okay, so you should see the Word document on my screen. So section 7.1 day 1 is on exploring exponential models. So we're going to look at what an exponential function is and be able to decide whether or not a given exponential function represents growth, meaning something is getting bigger, or exponential decay. If something's decaying, it means it's getting smaller. Okay? So that's going to be the goals by the end of today. Look at some graphs, look at some examples. Okay. First thing we want to do is kind of differentiate how is an exponential function different from something we're used to, like a linear function or a quadratic function. So just as a little warm-up, we probably saw these last year a little bit. Okay. A linear function, you see the word line in there. It just means I'm graphing a line. So if I wanted to sketch the graph of a linear function, this is just one example I could come up with. That looks like a nice straight line, as good as I can get. Okay. That's linear. When things are linear, typically they're going to be written in our favorite form, slope-intercept. Y equals mx plus b. Okay. Quadratic is when we have a power of 2, an exponent of 2. So typically this will be written in the form ax squared plus bx plus c. Okay. So really, how do you know if it's quadratic? You're going to see an exponent of 2. Okay. I'm even going to highlight that. That's how you know it's quadratic. If you see that exponent of 2. Okay. And it has to be on the variable, not on the number. It has to be on the variable. The graph of a quadratic function is a parabola, word you may not have come across for a while. But a parabola is just like a U shape. That's all it is. So this shape right here is a parabola. Okay. So we want to kind of move on from that and ask ourselves, well, what about something called an exponential function? And you got a little bit of an introduction to exponential growth if you watched the paper folding video I posted on YouTube. It's not my video, but I shared it with you. I thought it was interesting to see that it really doesn't take too long for you to fold a piece of paper in half over and over, and it gets thicker and thicker. I think it was 45 folds, and it's the distance from here to the moon. So that's what's cool about exponential functions is it doesn't take very long for it to grow very quickly or for it to get small very quickly. Okay. So let's look at another example. Paper folding is a good way to start. Bacteria multiplying is a classic example of an exponential function. So if we look at example 1, it says bacteria can increase at a fast rate when each bacteria splits into 2 new cells. For example, if we start with only 1 bacteria, which can double every hour, by the end of 1 day, how much bacteria will we have? Hey, a couple key words here I want to highlight. The first one is it's telling you that the bacteria are doubling every day. When you see the word doubling, that means that you're multiplying by 2 over and over again. I'm just going to put times 2. Okay. And we want to know the goal is at the end of 1 day, how many bacteria are we going to have? If you notice in the table, X is the number of hours, Y is the number of bacteria. 1 day, we need to be able to figure out how many hours that is. That's why you see 24 in the table at the end. That would be the end of 1 complete day. So if X is the number of hours, I got 0 hours, 1 hour, 2 hour, 3 hour, 4 hour, all the way up to 24. I start with 1 bacteria, and it continues to multiply by 2 every single hour. So 1 times 2 is 2. And then now there's 2. Each of those splits off. 2 times 2 is 4. Times 2 is 8. If I keep the pattern going, times 2 would be 16. Times 2 would be 32. And what's kind of interesting about this is you can actually write this with exponents. So if there's 1 bacteria, that's 2 to the power of 0. If I have 2 bacteria, that's 2 to the power of 1. 4, I remember, is 2 squared. 8 is 2 cubed, 2 times 2 times 2. Right? So really, what am I doing? I'm basically taking 2 and I'm raising it to the power of the number of hours that I have. So this one would be 2 to the 4th. Now I picked up one extra copy of 2. This would be 2 to the 5th, 2 to the 6th, 2 to the 7th, 2 to the 8th. And by the time I get to 24 hours, this would be 2 to the power of 24 because I have 24 copies of 2. We don't know what that is off the top of our head, so we have a wonderful tool called a calculator that'll do that for us. Oh, let's get to the home screen. 2, and then the exponent button you've used before is right above the division sign, power of 24. Oh my goodness, that's a big number. After one full day, you have 16,777,216 bacteria. So just like the paper folding to get to the moon, it doesn't take very long for things to grow very quickly if you're dealing with an exponential function. Okay? The next thing it wants to know is to write the equation that represents the pattern. Well, as we noticed in the table, we're picking up an extra copy of 2 for every extra hour that we pick up. So my equation would be y equals 2, and the exponent always matched the number of hours that I had. So my equation would be y equals 2 to the power of x. Let's graph it to see if it looks linear, if it looks quadratic, or if it looks a little bit different. So here's 0. Here's x. Here's y. This was our number of hours for x. This is going to be our number of bacteria for y. And we have the table to be able to plot the dots. At 0, I was at 1. I'm just going to put a dot at 1. Okay. After 1 hour, I had 2. After 2 hours, I had 4. So 2, 3, 4. After 3 hours, I had 8. So here's my third hour on the x-axis. I go up to 8 on the y-axis. Okay. And it's going to continue. The gaps between the dots are going to continue to get larger and larger. So if I sketch this now, connect the dots, it's going to continue to grow faster and faster. Okay. So does it look linear? It's definitely not a straight line, so this is a hard no. Does it appear quadratic? It's kind of U-shaped. We just don't really know what it does on the other side. And I'll kind of spoiler alert, okay? If you were to go into negative powers, what would happen is this would actually continue to come down without ever actually crossing the x-axis, but it's never going to come back up again. It's just going to continue to get smaller and smaller as I move off to the left. So does it appear quadratic? Maybe let's just put a little bit. Okay. And if we were to describe this graph, as x gets bigger and bigger, as I move farther off to the right, the y values continue to get bigger and bigger as well. So as x gets bigger, y also gets bigger. Okay. All right, moving on to the second page. We want to actually look at the format of these exponential functions. So that's the type of function that we're looking at, is called an exponential function. And it's written in the form y equals a times b to the x. Sometimes you might see it written with a dot in between the a and the b. Sometimes you might see it written with a parenthesis. All of these forms are dealing with an exponential function. And here's a little clue. Don't tell anybody else. But the way you can tell it's an exponential function is because x is the exponent. Anytime you're dealing with an equation and you see x as that little guy in the sky, you have an exponential function. Okay. So how can we remember this? X is the exponent. The exponent is not a number, it's a variable. Okay. That's how you can remember. So how do I know if it's going to be something that gets bigger or if it gets smaller? We want to be able to decide if something's growing, getting bigger, or decaying, getting smaller. It's all about the b value, which is the base right there. It's all about that base. It's like the song. So to decide what type of graph you're going to get, look at the B value. If that B value is bigger than 1, that means you're multiplying by a number that's bigger than 1 over and over. That's going to make things larger. That's what we call exponential growth. When that B value, the one that's right underneath the X, is larger than 1. And the graph looks very much like what we did on the first page. It starts growing very slowly, and over time it gets bigger and bigger. Okay. B is what we call the growth factor. It's like the multiplier. Okay. It's what you're multiplying by over and over again. And as we said on the front, as X gets bigger, as X increases, the value of Y also increases, which you can see on the graph. Okay. So in the example we did on the front page, we had Y equals 2 to the X. If I want to write it in the form A times B to the X, I don't see a number in front of the 2, which means that it's assumed to be a 1. It's that ninja 1 that we often don't write. So I could just write this as Y equals 1 times 2 to the X. Okay. And now I can see my A value is 1. Your A value is the starting value, okay, which on the graph, here's where you start out. The starting value is the value of Y when X is equal to 0. Okay. So here's my A value. And then my B value is the one that's getting raised to the power of X. So B in this example would be 2. That's my multiplier, my growth factor. The y-intercept, okay, is always just going to be the same as your starting value. That's what a y-intercept is. It's your starting value on a graph. Okay, so when X is equal to 0, we can test it out. If I plug in 0 for X, I get Y equals 1 times 2 to the 0. If I use the order of operations, I have to do exponents first. Anything to the 0 power is just 1. So this would be 1 times 1, which is 1. So my y-intercept is at 0, 1. And oh my goodness, the y-intercept and the A value match. That's always going to happen. Your y-intercept is always just your A value, which is the number that's not being raised to the power of X. Okay. So let's even write that down. The y-intercept is always A. Okay, so it's very easy to spot. Okay. And on your graph, it's right there. There's your y-intercept. That's your A value, the green dot. Okay, so if B is bigger than 1, it's growth. But if your B value is between 0 and 1, maybe like a half or a third or 0.4, that's what we call exponential decay. Because what happens when you start multiplying by, say, a half? If I take 16 and I multiply it by a half, it turns into 8. If I take 8 and I multiply it by a half, it turns into 4. The numbers are getting smaller now. As X gets bigger, Y is going down. That's decay, whereas growth would be, it's the best whistling I can do tonight. Okay, so exponential decay, things get smaller. B is what we call a decay factor now. Okay, things are getting smaller. The graph would look like this. Starts out very large, over time, gets smaller and smaller and smaller, never actually crosses that x-axis. But over time, it starts decaying a little bit more slowly. Okay. So it's got like the opposite look from the graph that we did up top. Okay. You can notice that as X moves off to the right, as X gets bigger, Y is getting smaller. We started up here, we're going down, 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 down. As X increases, Y decreases. Okay. So to decide if it's growth or decay, it's about the B value. B is bigger than 1, growth. If B is between 0 and 1, decay. And A always gives you the starting value, okay, the y-intercept. Let's look at another application. We did an example with bacteria, which was exponential growth. I always think a good example of exponential decay is like a tournament where 2 teams are competing and only one can win. Okay. Most classic example is the March Madness tournament. Okay, 2 basketball teams play, only one can win. Every single round of March Madness, half the teams are eliminated because half of them win and half of them lose. Okay, so let's just use that as an example. Each year you host a basketball tournament. Okay. Play starts with, let's say, 64 teams. So there's your starting value. Okay, I'm even going to underline that. Starts with 64 teams. They're telling you the starting value. During each round, half of the teams are eliminated, which makes sense because one of them is going to win and one of them is going to lose. Fill in the following table for the other 5 rounds. So X is our rounds and Y is going to be the number of teams that we have left. So round 0 is the start of the tournament. There's 64 teams. If half of them win, I'm going to multiply 64 by a half, which really just means I'm dividing it by 2. So now there's only going to be 32 teams left. And then I'm going to multiply it by half again. So I'm going to divide it by 2 again. Now there's only 16 teams left. Half of those win. In the next round, there's only 8 teams left. Half of those teams win. 4. And then finally, from those 4 teams, the final 4, 2 of them win. Now you've only got 2 teams left. Okay? So if we look at this graph, it starts way up at the top at 64. So here's X, here's Y, here's 0. Way up at the top, I got 64. And then after round 1, let's just cut it in half and put 32 here. Here's 32 teams left. Round 2, so here's 1, here's 2, 16. So I'm going to cut that in half again. And then after round 3, cut it in half again. There's 8. And you can see what's going to happen is you're going to get an exponential decay in this case. Okay. Keeps going down, 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 down. There's my graph. What's the starting value? Well, that's what we labeled in the original problem. We started with 64 teams. And that would make sense because on the graph, my y-intercept is at 64. And as we said, our a value is always the same as our y-intercept. So a is equal to 64. Since as x gets bigger, the y values get smaller, this would be exponential decay. What's my multiplier, my decay factor in this case? Well, every single time a new round happens, half of the teams are eliminated. So I keep multiplying by a half. So b is 1/2. That's my decay factor. That would make sense it's decay because we said to be decay, the b value has to be between 0 and 1. 1/2 is less than 1, and it's bigger than 0. So the equation, remember, is y equals a times b to the x. A is that starting value, so there's our 64. And my b value is my multiplier, my decay factor, which is a half. And so I'm going to raise it to the power of x. Okay. One quick comment I want to make. Please never, ever, 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 ever multiply these two numbers together, because otherwise you're breaking the order of operations. You can't do multiplication before you do exponents. So as tempting as it is to want to multiply 64.5, please don't do it. Okay? Otherwise, you're breaking the math law. Don't do that. Okay? Leave it as 64 times 1/2 to the x. Okay. So before we do the next set of examples, again, just as a reminder, an exponential function will always fit this form, y equals a times b to the x. Okay. And how do we remember that? One more time. X is the exponent. Okay. If you see x up in the exponent, you automatically know it's an exponential function. So we want to identify now, is the given equation linear? Is it quadratic? Those are the two we did in the warm-up on the front page. Or is it exponential? And if it is exponential, we want to decide, is it growth or decay? Okay. And remember, how do you decide growth or decay? It's all about that base. It's all about the b value. Okay. So in the first one, oh my goodness, x is an exponent. I automatically know it's exponential. And the value that I'm looking at to decide if it's growth or decay is not the starting value. It's the one that's being raised to the power of x. So there's my b value. Okay. I'm going to save this so we don't lose it. Quick pause. Give your brain a stretch break. Maybe it'll let me keep writing. Let's try it. So think for yourself, okay, there's my B value, 0.95. 0.95 is less than 1. If you look back at the previous page, if you multiply by something less than 1, if that B value is less than 1, that's going to be exponential decay. Okay. And that's because, I'm going to write it, it's because B is less than 1. Okay. In the second one, I still see x up in the exponent, so I know it's exponential for sure. But this time my B value is equal to 4, which is bigger than 1. If you multiply by something by 4 over and over again, it's going to go exponential growth. Reason? Because my B value is bigger than 1. Okay. In the third one, x is an exponent. So this is exponential. Okay. And before I tell you, I want you to think about this one for a second. Which number is going to help you decide if it's growth or decay? Is it going to be the 10 or is it going to be the 1/3? Okay, so if you want, pause the video for a second. Think to yourself, which number is going to help you decide? And then write down if it's growth or decay. Okay, so what you should have come up with is the 1/3 is your B value. And since that's less than 1, this is exponential decay. So that's because B is less than 1. Letter D, immediately I see x is not an exponent, so it can't be exponential. And it's also not quadratic because it does not have a power of 2. This is straight up written in y equals mx plus b form. Okay, as clear as day. This was probably the first type of function you ever learned to graph. Okay, back in the good old days, this is linear. Okay. Okay, the next one, I see a power of 2. Okay, there is an exponent, but it's not the letter x. In order to be exponential, it has to be the letter x up in the exponent. If you have a power of 2, that's the definition of what it means to be quadratic. And I'm even going to highlight that here. It's because of that little power of 2 up top. Letter F, okay, warning, it's a little bit sneaky. Okay, even though it's not written in this form from part E, this is still quadratic because it has a power of 2. And the way you can get it to look like this form is you could FOIL this out. You don't have to, but you could do 4x minus 5 times 4x minus 5. Okay. And if you do some FOIL, you would get 16x squared. You'd have minus 20x. Minus 20x would be minus 40x. And then negative 5 times negative 5 would be 25. Okay. Again, you don't have to go through all the work in this problem for that. I immediately can tell that it's quadratic because I have something in parentheses raised to a power of 2. If you see something in parentheses, have to have the parentheses, raised to a power of 2, okay, then you're going to have a quadratic graph. Okay. Letter G, notice there is a power of 2, but it's not on the letter x. So you're not raising your variable to a power of 2. You're just raising 7 to 2. 7 squared is 7 times 7. That's 49. So this is really just a fancy way of saying y equals x plus 49. And again, that's mx plus b. That's linear. Okay, h, I, and j are a little bit more application based. If you're walking at a constant rate of 5 miles per hour, that means every time your hours go up by 1, your miles go up by 5. Okay, so up 5 over 1, up 5 over 1, up 5 over 1. Okay, constant rate. If you ever see that phrase, it's linear because linear functions have a constant rate of change. Okay, so this one would be linear. Okay, and the key word that told me that is it said constant rate. 7 multiplied repeatedly. It's like our bacteria from the beginning example from the front page. In that one, it was multiplying by 2 repeatedly. Here we're multiplying by 7 repeatedly. Anytime you have something that's being constantly multiplied, that's going to be an exponential function. Okay, because the pattern is based on multiplication. That's what your B value is. It's your multiplier, your growth or your decay factor. Okay. So my key word in the first one here was constant rate. My key word here is multiply. And for J, it might help to draw a picture. What's the path of a punted football? Okay. You kick a football, it's going to go up in the air. Do my best drawing of a football. There's the football. You can probably do better than I can. I'm not an artist. Kick it. Here's you kicking it. Apparently your foot is like 10 feet long. Kick it up in the air. What goes up must come down. Football comes back down. Hopefully somebody intercepts it and runs to the touchdown line. Touchdown. Okay, I'm done. Anyway, you can see that that path is definitely not exponential because it changes direction. It comes back down. It's not linear. It makes that U shape, that parabola. So this is quadratic. Okay. All right, last couple at the bottom. Got a couple more examples. I want to show you how to graph these on the calculator. But even without the graph, at this point, you should be able to decide from the ones we've done before what the y-intercept is just by looking at the equation and whether or not it represents growth or decay. That's something you should be able to decide without the picture. Okay? And there are some problems on your homework worksheet like that. Okay? So let's do part A together, and then I'll have you try out part B. Okay? In part A, we have y equals 10 times 3 to the x. My y-intercept, remember, that's my starting value. I'm going to write what letter that is next to it. That's always going to be the letter A. Okay. My growth or decay is going to be determined by the letter B. So A in this problem, remember, that's the one that does not have the exponent. A is 10, and B is the one that does have the exponent, the little x up top. In this problem, B is 3. Okay. So my y-intercept, my starting value is the A value. That's 10. Okay. And my growth or decay, well, since B is bigger than 1, this one's going to be growth because my 3 is bigger than 1. Okay, so on the graph, I am going to put the y-intercept on there, which is at 0, 10. Remember, it's a starting value, so it's always when x is equal to 0. So I definitely have one dot on the graph that I can put. And if I want to get the others, what's awesome is I can just use my TI-84. So I go to the home screen, I go to y equals, and I'm going to type in the equation. 10, as I see it, open parenthesis, 3, close parenthesis. And if I want to raise it to the power of x, you have to hit the little upside down V button. That's the exponent button in the right column. And then x is located right next to the word alpha in the second column. So right where my cursor is hovering. So make sure you have that on your screen. And you can get a little rough sketch of what it looks like. I don't want you just graphing it from the screen, though. I want you to pick at least 3 dots. You should have always at least 3 dots on your graph when you're doing these. And the way that you can get the dots is by going to your table. To get your table, you go to second, graph. Okay, so hit second first, hit graph. And we already found 0, 10 was a point. Looks like if we go past 0, the numbers start getting too big. 30, 90, we don't have space for. So let's do some negative numbers. Looks like at -1, it's at 3.3. At -2, it's at 1.1. So let's plot those. Okay. -1, it's at 3.3. So about here. And then if I scroll up, -3, it's at about 0.37. So we'll call it about 0.4. Uh-oh, my dot moved. Where'd my dot go? Where'd my dot go? -2, I said was at, or no, -1 was at 3.3. There we go. And then at -2, it was at 1.1. It's about there. And I'm going to add one more dot. You don't have to, but I like to make my graph a little bit more accurate. So I'm going to go at -3. It's at about 0.37, 0.4. Okay. And the key here is when you connect the dots, make sure that you do not cross the x-axis. Okay. It's going to continue to get smaller and smaller, but it's not ever going to actually cross the x-axis. So there's my graph. Connect the dots. There we go. I'm going to make the dots a little bit thicker so you can see them. There's 1 dot, 2, 3, 4. Hey, and that makes sense. It looks like exponential growth. As I move off to the right, as x gets bigger, y gets bigger as well. Okay. Part B, I want you to try yourself, and then once you're done and you have a graph, I want you to check it. I'm going to walk through it. I want you to actually check your work to make sure that you got that one. Okay. And after that, that's it for the video. You can go and start your worksheet assignment, which is going to be due next class period. Okay. All right, so hopefully you've had a chance to try and work through that one. For part B, let's label first. My A value in this one is 5, and my B value is 0.8. Make sure you notice there's a little decimal place right there. So the y-intercept, remember, is your A value. So the y-intercept in this one's going to be at 5. Okay. Or if you want to write it as an ordered pair, you can write it as 0, 5. Growth or decay is determined by the B value. The B value here is equal to 0.8. Since that's less than 1, this is going to be decay. That's because B is less than 1. Okay. So to graph this one, the y-intercept I can add on the graph right away. There's my dot at 0, 5. To get a couple other dots, let's go to y equals. Clear out the equation we had, and I'm going to type in the new one. So 5, parenthesis, 0.8, close parenthesis, to the power of x. So there it is typed on the screen. I'm going to go just get a basic idea for what it should look like. We want to actually get at least 3 dots. I already got one of them done on the table. I got the y-intercept. So I go to second graph. And this time it looks like I can fit something to the right. So at 1, it's at 4. So let's add that. At 1, it's at 4. And then at -1, it looks like it's at 6.25. So at -1, it goes up 6.25. That's about there. Okay. And maybe I'll add one more just for the heck of it. At 2, it's at 3.2. It's about there. Okay. And if it's a decimal, just, get as close as you can. It doesn't have to be perfect. Our eyes can't perfectly detect those decimals. But I can already tell the dots are going down, which makes sense that it's decay. And so this continues to go down, 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 but it doesn't cross the x-axis. It gets ever so close to it, but it never crosses it. So sad. Okay. All right, so there would be my exponential decay graph. Okay, so I'm just going to make a comment here. Use at least, I can't type or can't write today, can I? Where's my eraser? Use at least 3 points on your graph. Just as a rule of thumb, that'll get you a good enough rough sketch of what you need. Okay. All right, so that'll do it for these notes. Have a good rest of the day.